This is our introduction to diagnostics. We want to get you started and give you some general principles we're going to apply to all the different systems we'll be talking about. So here we sit with our module. We have no communications, but the signals we're looking at are normal at the module. Yeah, don't worry about it. We're going to get into it much deeper later. I want to give you a preview of what we're going to do. So how do we handle this? What are we going to do? Well, first of all, if they're good, we have good power and ground, we're going to repair or replace the module. But before you do that, here's another example. The module that is making decisions that are not logical. Well, check for technical service bulletins. We cannot say it enough. There are some cases where nothing but a technical service bulletin will replace an unlimited amount of information. Other cases, you've got to remember something. When replacing modules without programming them, you can introduce new problems without fixing an existing problem. Let's say that again. Remember, replacing modules without programming them can introduce new problems without solving it. I can't tell you the number of times we've gone out on communications problems to find out, well, I had a code, so I stuck a new module in. It was a GEM module on a Ford. Well, did you reprogram or flash program the GEM? No. Well, you know what GEM stands for? GEM stands for Generic Electronic Module. It is generic. Its personality is adjusted to the vehicle. You use J2534. It's the specifications for using low-cost hardware to program all programmable modules on all vehicles that use flash programming. Let me say that again. You can get low-cost hardware that plugs between a personal computer hooked to the manufacturer's internet connection, and you can program all the modules on all the cars using flash programming. Now, that's required by the EPA. This is here so you can do it. But if you're going to replace modules, you need to be doing programming. It uses the same communications protocols to do this flash programming that we're going to be covering in this program. So that's really important to you, because you've got to ensure that communications are normal before attempting to flash program modules. If you're getting garbled communications, you're not going to get a good program. So keep that in mind, that you're going to need good information. It comes down to knowing what is normal. And we're going to show you that. Don't worry about it. Then we're going to show you how to isolate the cause of the problem. Now, one of the reasons we're showing you this picture is this particular point in time is I want you to realize this is not a quick 1-hour diagnostic. If you're going into this with a notion you can diagnose communications problems in 1 hour, stop right here. You're not going to get there. This was a vehicle we had to capture and thought the picture's worth 1,000 words. This is not uncommon to see when someone is working on a vehicle that's been in a collision. The dash looks like this, because we have frequently broken wires in damaged modules. So this is not an uncommon picture. But let's get back to our diagnostic. Why won't your scan tool communicate with a PCM? This is the information that relates to scan data and other communications problems. But it's the basic thing that you all are familiar with, the scan tool. Why do modules fail to communicate with each other? What's the cause of it? We're going to answer some of these questions. And the first thing we got to do is, how does communication systems identify a problem? How do they know they have had a problem? Well, we're going to give you a quick overview here, and we're going to start with a circuit from a PCI diagram. Now, this could be something off of a Volkswagen. It could be something off of a GM. It could be something off of a Toyota. It could be a Hyundai. Pick a world, pick a country. There's applications. This one happens to be off of Chrysler, but it doesn't matter, because they're all going to work in a similar manner. The purpose of this circuit is to supply signals to the bus and to read signals on the bus. It's a two-way street. It's called a receive-transmit. Now, the purpose of the bus, as we call it, is to allow multiple modules to communicate with each other over a single set of wires or a single wire. That's an important. We've reduced the wire count, and we're going to show you examples of that more along. For these to talk without bumping into each other, it's going to require a priority system to allow them each module to have time to talk. In this particular case, we have 2 buses. The blue one is the K bus. That's where we're going to be talking. And in this particular case, not everything is shaded in. We just shaded in a few of the blue lines. And as we said, 15, the K line just starts the talking. So all these modules on one of those buses would look something like this. The signals on the bus are identified as either dominant or recessive. Now, that sounds really strange. Everybody's talked about digital signals being high or low. Why don't we do that here? Well, we're going to have to show you something, because high or low isn't necessarily dominant or recessive. Let's see what we're talking about here. The communications protocol we use by the vehicle will determine whether high or low is dominant. We're going to use a CAN signal. This is high-speed CAN made up of 2 wires. One wire is called CAN H and one is called CAN L. Now, don't confuse CAN L, CAN H with high-speed CAN and low-speed CAN. We have 3 flavors of CAN when we get there. We've got low speed, medium speed, and high speed. This is the high-speed CAN. Meaning a pulse like this is going to take about 2 1/millionths of a second. The pattern like this comes when you got your sweep rate at about a half a microsecond per division. You'll get a trace that looks something like this. But let's examine this trace for a moment. When both signals are near 2.5 volts, the circuit is at rest, also known as the recessive state. In earlier versions, it was called the passive state. We're going to continue with recessive state, just because we keep stumbling over passive recessive. In the dominant state, the CAN H signal goes high, while the CAN low signal goes low. Now, there is the point we're making. If you know the protocol, the normal operation, which is what we told you're going to have to learn to look for, CAN L will go low when it's dominant. CAN H will go high. That's going to become important, because that's how we're going to let these modules talk to each other. They're going to, dominant means when you, as a module, go dominant, you're saying you want to talk, and everybody else will stop and listen to you. And we'll talk more about that later. But when a mode wants to send a message on the bus, it checks to see if the bus is recessive or dominant. If it's recessive, you can talk. If it's dominant, you can't. Then the module outputs a dominant signal that lasts for several internal clock or timing cycles. The width of this dominant is where priority comes in. Wide ones have higher priority than short ones, because anybody looking out there who sees a dominant signal, who wants to talk, will shut up and wait and listen. So that's a very important issue, and we'll see how that works a little more later. The module waits for a recessive cycle that lasts for several cycles, then starts sending information. Remember, you're going to need to know the communications protocol to determine which level is dominant and recessive for all of these different systems, and we're going to show you. That's why we have training selections for each one of these, so you only learn the one you need to work with now, because it changes all the time. Remember, the module listens with the receive circuit to verify their transmits. We're wondering how these things know they've made a mistake. Well, it sits here and says, I want a dominant signal. I'm transmitting dominant. Then it says, did I read a dominant? This is called data verification. It verifies its own messages. Now, if it can't verify its own messages, if the received signal indicates the wrong signal is being sent, the module pauses for a while. This pause is used to check to see if another module is talking. If it is, this is called a data collision. A collision happens when 2 ECUs start talking at the same instant. Whatever happened, and it shouldn't, the priority system should minimize this. This is a very rare occurrence. Different priority systems are used to allow different ECUs to take control of the bus. Some things have higher priorities. Some modules, as you see on the bottom of this, we have some modules that are dominant. They will take control of the bus where standard modes won't. But it is still going to be using a dominant signal, a dominant module merely means it will dominate all other modules. Now, if an ECU always has the wrong signal level, if it's always wrong, it'll take itself offline as possible. And this will usually generate a U code because it will not be able to communicate with other modules. So as you can see, failures like this result in the ECU hanging the bus high or low. It's going to shut the whole bus down. So we've got different classes of failure. We got one module that identifies that it can't talk, takes itself offline, quits talking. The other modules set a U code. Then we have situations where nobody can talk because one of the modules have gone bad. That's what we're going to be trying to show you in this program. Each protocol has its own set of rules that we'll be discussing to help you determine and isolate these things. But in order to diagnose a problem quickly, you need to understand the different communication standards, and we're going to go back and talk about that. But something we want you to remember, nothing explains everything. A different vehicle may not operate the same as the last one you just tested. Don't think because you know something in one place, you know it everywhere. Each communication circuit becomes a standalone entity that you're going to have to diagnose. And sometimes there are holes in communications programs where only a TSB will help diagnose the problem. We've said it before, we're saying it again. We'll give you a good example. A few years ago, BMW 3 Series. If for some reason the ambient air temperature sensor was disconnected, communications was shut down to the instrument bus. Now you could go and look and do all kinds of things and testing, and you will never get there. No amount of diagnostics is going to find this hole in a program. So use TSBs. We recommend that you go on the manufacturer's website when you have a communications problem and make sure you're not butting heads with a TSB when you find a problem. It's happened before, and it'll happen again. So before you get too lost in the diagnosis, and we're going to have diagrams like this you're going to be looking at, we want you to do the simple things first. Don't get too deep in diagnosis and ignore the basics. If your scan tool won't communicate, start off by just trying to decide what's going on. Now, here's some research we did. When they wouldn't communicate, vast majority of the times, with a small sample we had, 86% of them were because the guy did something wrong with the scan tool. Only 14% were actually caused by a vehicle problem. They had the incorrect model year program. They had the wrong manufacturer. They were lying about the model year. They had the wrong bin code. They had cables and adapters that were broken, bad, misapplications, whatever. But here's some things you can do. We're going to use the Genesis for example. You come to your application manager opening screen, scroll down till you get the system setup, and hit enter. So when you get here and hit enter, it's going to take you to a whole list of things. Scroll all the way down to the bottom where it says technical support and highlight that and hit enter. Then go to the bottom of that list to file system check. Now get ready to stand here for a while. This takes minutes and minutes and minutes. It's defragmenting the memory, straightening everything out, and it's checking to see if it's found anything wrong. Now, if it finds something wrong, eventually, and don't get discouraged, let this thing finish, it will come back and say, hey, I found an improper shutdown. This just means it's fixing any problems you may have had. You've seen similar things like this on your screen for your computer where it said it was shut down improperly. If you have anything like this, this is a good first step. Use this in your scan tool to make sure everything is up to speed. So when we get down to our communications, what are we talking about in communications? It's between electronic control units. We call them ECUs. You hear us use term jargon, modules, all too frequently. But this includes all of the modules and the wiring. This is all part of a communication system, and you have to address it. And we need to find some terms before we go into using it and get too deep into this. Technically speaking, baud is the maximum possible time per second the carrier signal could change states. It is not how many bits per second the modem is transmitting. There are more than 2 states to a signal, and that no signal would use the maximum total number of bits during a transmission. The circuits we're talking about are broken down. Serial have send and receive signals on one wire. Differentials are twisted pair, and they need 2 mirror images of each other to work. Parallel send and receive are on different wires or different combinations. So let's concentrate on what we got to do in the service bay to start diagnosing cars and start thinking about diagnostics. Remember, we're still on the easy things first. Getting back to your scan tool. Which data are you having trouble with? Go in and see if you can access each one of these. Can you see the body computer, security, see the transmission, ABS, engine, PCM? Try to communicate with each module. If your scan tool supports pinging, like some of the imports do, go ahead and do it. See if you can identify which modules are not talking. But if you have one of those circuits we're talking about where everything is dead, pinging isn't going to do any good. Some other scan tools have what they call a status report. If you have either one of these, go and get it. Otherwise, take your scan tool and program it to talk to the computer. Can you get in? Can you get in and talk to the transmission? Can you get in and talk to the ABS system? Can you talk to the body computer? Can you talk to the ABS monitor? This particular one has a status report we'll show you. This says nobody's talking. We got a major failure. Bad things have happened. What do you do when no one is talking? Well, that's what we're going to show you in this training program, how to go about diagnosing them. Let's say part of them are talking, but not all of them. Start adding up the other clues you have about the vehicle. Do you need the body computer to be communicating for the security system to work? Let me say that one more time. Every day on IATN, I see somebody saying, I got a car that won't start. What do you think it could be? And they get a lot of suggestions and very few answers. It says, do you have communications? No, I've got a U code. Duh. If you don't have communications, your security system, if that's the bus that's down, may not be able to talk. This is a big part of the situation. So keep this in mind. Look at all the clues you're going to be looking at. Stay on the easy things as long as you can. Don't get carried away too quickly. There's a bear in the woods we need to tell you about. The OBD2 Diagnostic Link Connector, or Diagnostic Communications Link, or whatever you want to call it, isn't really universal. We're going to show you some rules, what it's supposed to be there, but if you look at the schematics we're looking at, this bear in the woods runs up and bites you if you're not careful. It's not always the way it's supposed to be. Now, one of the prime examples is we look at the ALDL connector and start talking about different pieces of it. We find that 16 is battery, B+. That's a good place for you to get B+ if you need it and check to see if the scan tool is getting proper power. Sometimes that's a reason for the failure. Now, pin 2 can have a couple different things. It has GM Class 2 data, and that is fairly universal in GM. That's the good news. It has half of the Ford SCP system. Why do we keep talking about all these different systems? Because Ford's SCP has got 2 lines. GM has 1. Chrysler's newest generation, before CAN, is going to have PCI on this pin. Then we go to 10. GM doesn't use it. Chrysler uses it at times. At times it doesn't use it. It's usually used for flash programming or something, or communicating with some extra modules if it is used. But Ford uses it for their SCP, the other half of the data signal. Pin 7. GM doesn't use it, but Ford uses it for the ISO bus. And fortunately, you're going to find that other people use it for the ISO bus. 13. GM doesn't use it, but Ford uses this for their module programming signal. And in Chrysler, it's either not used or has some unlimited special usage. Back to that 7 again, we find ISO 9141 and KWP 2000, which is the 14230-4 K line. That's used there on most European and Asian cars. Fairly universal. 15 is not universal. You'll find times you've got battery voltage on here. And where it is used, it's used with 9141 and 14230, which is on the Asian and European imports. 6 is new. Good news. Finally, global CAN high. ISO 15765-4, and this they're going to enforce, they say. CAN global again. CAN low. Remember, this is not high speed, low speed. This is talking about what signal is dominant. Global chassis ground. These are not global because sometimes you see the two of them tied together, but 5 is supposed to be a low current ground. 4 is supposed to be a high current ground. So when you see something like this, it never exists, but this is theoretical. This is a section from Chrysler's publication saying this is what's going to be used. The minimum you should look for is this minimal amount of work here. It tells you what buses are on there. And remember, circuit problems that cause a loss of scan data, ground is almost 80%. Power is the other part. Now, that's a circuit problem with this. Is there B plus here? Get it down basics. Don't assume your scan tool has a problem just because it won't work on this car but works on another one. It may be something as simple as B plus is missing. Are all the DCL, the grounds good going to the data communications link? These are the type of things you need to do before jumping into the fire. And the first thing we're going to tell you, before you jump off the bridge and think you know what's going on, you must gather vehicle-specific information. Now, this is one we used in our shop out there because the shop we're working in had an inkjet printer, and as you can see, we touched it before it dried. This is the bare minimum. And when you get it, kind of look and see what you're looking at here. It tells you what's there. Study it. Know what signals you're looking for. This is far better. We are big, big fans of something unique to Mitchell. Mitchell goes to the trouble to make this kind of diagram up for you. It is worth its weight in gold, and you're going to see us using it all through our diagnostic. It shows us where PCI buses are and SCP buses and different things. This is one of the buses we're looking at. When we say there's a lot of different modules in a bus, take a look at this one. This particular one here happens to be off of a Volkswagen. It's got a lot of places it goes. So pay attention. Find out what's happening here. And you're going to find sometimes you're going to have the 9141, like we looked at before. This is the same diagram we used for 9141. It's also got CAN on there. We have to go into the data more, and we can find individual CAN buses. Notice we have two lines here, CAN L, CAN H. We've talked about that. This is a high-speed system. This is a star connector, and we're going to talk about that a little more. We're going to show you how to work on this Chrysler that's got 25 ECUs. 25. And yes, it can be broken down so we know what's happening. But just remember, modules are going to talk to each other. Here's a steering column trying to address some information to the front control module. But remember, every one of those twisted pair wires gets the same signal. Now, this particular module talks on two different buses. It also talks on the low-speed bus because it talks to all the modules on the bottom as well. So every time any module tries to talk, it addresses everybody across the whole board. We're going to talk about star configurations. The SCI on the bottom is a set of pair of wires that run back and forth between the data link connector and the PCM. But the PCI at the top, all of them joined together in a couple different splices. We got 3 of them there. When something goes wrong, we can have problems that mess the whole thing up. And as we're going to say one more time, there's a bear in the woods. You're never going to see pin uses follow everything it's supposed to. Look down there at the bottom of this. It says pin 15 is SCI transmission, transmit. the spec says it should be not used. It's for ISO 9141-2. So we keep saying it. But now you're ready to go to the individual communications protocols. Now, what we're saying is, when you go to ISO 9141, we're going to show you the Asian and the KWP 2000 that's using Asian and European imports. When you go to Chrysler, we'll break down what they use. And we have to do that because, fortunately, the Asian and European stay standard. It's the U.S. cars that have all the different versions. So you'll have Ford, GM, and Chrysler broken down differently. Go to those individual protocols and see how they work. Make sure you take time to go look at CAN so you're ready for the system that's going to be on every single vehicle later this year.